Welcome to the class. Dear students, today we are going to see what is Wittig's reaction. To understand Wittig's in this class, what we will see is what is Wittig's reagent first, and then we will see how to prepare the Wittig's reagent. Only then can we understand the Wittig's reaction and its mechanism. And finally, we are going to look at the significance of Wittig's reaction. So let us start Wittig's reaction. To understand Wittig's reaction, we have to first know what is a Wittig's reagent. The Wittig's reagent is also called as organophosphorus ylides or simply ylides. It's called as organophosphorus ylides or simply ylides. So what is ylides? Let us look at this. Ylides are organophosphorus compounds. This is an organophosphorus compound, right? It's an organophosphorus compound. It's an organophosphorus neutral compound, okay, in which adjacent atoms which are covalently bonded to each other are having positive and negative charge. It's fine. So overall the molecule is a neutral molecule. What did I say? I said organophosphorus ylides or simply ylides are organophosphorus compounds in which adjacent atoms which are covalently bonded to each other are having positive and negative charges. So overall the molecule is neutral. Okay, to understand, let us now go for the preparation of ylides. But to understand the preparation of ylides, we need to know the atomic number of phosphorus. Atomic number of phosphorus is 15. So if we are going for its electronic configuration, it would be 1s2, 2s2, 2p6, 3s2, 3p3, 3d. Okay, there is nothing, no electron in this orbit. Okay, so if I am drawing it like this, I find out that there are 3 valence electrons of phosphorus. That means there is the valency of phosphorus is 3 and there is one lone pair of electron. Okay, so it can accept 3 electron more. If it accepts 3 electron more, it would attain octet configuration in outermost shell. That means the configuration of argon. Okay, this is case number 1. In case number 2, what can happen if I am heating phosphorus? That means if phosphorus is getting activated, then what would happen? One electron from this orbital, from the 3s, this is the 3s orbital, from the 3s orbital, it can jump to 3d orbital. In that case, the configuration would become 3d1. But in that case, in place of 3 valence electron, there will be total of 5 valence electrons. That means it could accept 5 electrons more. It could accept 5 electrons more. If it accepts the 5 electrons more, then phosphorus atomic number will become 20. Okay, that will be equal to atomic number of calcium. In that case, it would not attain inert gas configuration. Okay, so that is what I am trying to say is phosphorus has 2 valencies. 3 valence, there is valency 3. In case if there is the valency is 3, there will be one lone pair of electron. It would be able to accept 3 electrons into its orbital and achieve the octet configuration of argon. Okay, and in another case, if phosphorus is becoming activated, then one electron can jump from the 3s orbital to the 3d orbital. It would have 5 electrons as valence electron. It could accept 5 electrons, but then in that case it would not achieve the inert gas configuration. It would achieve the configuration of calcium, which is 20. So that is this is understandable. That is, there is valency 3 and it has got 5 valency. So phosphorus has 2 valencies. Number 1 valency 3. In that case there will be one lone pair of electron, and number 2 valency can be 5, but in that case there won't be any lone pair of electron. If the valency is 3 and if there is a lone pair of electron, it can achieve octet configuration in its outermost shell. So now let us now go for the preparation of ylides. As I said, ylides are organophosphorus compounds, atoms of which are bonded to each other by covalent bond, and they are positively and negatively charged, and this is at adjacent positions. Now let us understand the preparation of halides. For preparing halides, I take phosphine, triphenyl phosphine. This is triphenyl phosphine. Okay, all its valency is full, correct? It has accepted 3 electrons and made covalent bonds with C6H5. So its valency is full, and plus it has got a lone pair of electron. Okay, this is triphenyl phosphine. Its octet configuration is complete. And I take any alkyl halide which is having at least one alpha hydrogen atom. Okay, so at least one alpha hydrogen atom. So one alpha hydrogen atom, secondary alkyl halide. Okay, and fine. So that means tertiary alkyl halide won't show this reaction. Okay, they can't go for preparation of Wittig reagent. Secondary alkyl halide can go and primary alkyl halide can go. Ethyl alkyl halide and methyl alkyl halide definitely can go. Okay, but tertiary alkyl halide cannot show this preparation. So I am taken here secondary alkyl halide. Let us now see what happens. So if I am giving a little bit of heat here, what would happen? This bond is already very fragile bond. This is polar in nature. It would break. So when it breaks, Br would become negative and this would become positive. The alkyl would become positive. That would join with this. It would take the lone pair of phosphorus. Correct? So now let us see what happens. So this is the result. C6H5 3. Because it has lost its lone pair of electron, it has become positive in charge. Okay, in this case also phosphorus is, its octet is complete because it is having its 3 valency is already been occupied by phenyl group. Correct? It has only given its lone pair of electron. So its octet is complete. It doesn't affect its octet. Fine. This hydrogen, let me write this hydrogen like this. Now treat it with NaOH. Now there is a Br minus here, right? That Br minus is in close association with this compound. Okay, it's not formed any bond. It is not forming any bond, but it is in close association with this compound, which is an organophosphorus compound, because it is having a positive charge. So it is near the vicinity of this positive charge. That's it. But there is no association. Fine. Now when I apply NaOH, this is becoming Na plus and OH minus. The Na plus part takes the Br and it becomes NaBr. And OH minus, what it does, it knocks out the proton from here. Okay, when OH minus knocks out the proton from here, what would happen? A pair of electron will be left here. Fine. So 2 things will come out. What it be? One will be NaBr, the other will be H2O. And what would be the result? Let us see. R C minus P plus C6H5 3. So this is what we get, right? Because H has been knocked out by the base, the pair of electron has been left in carbon, and this pair of electron now it is in carbon. Okay, look at this halide. We have formed the halide. Look at this halide. Is there any issue with this? See, phosphorus, is its octet complete? Yes, it is complete. The octet is complete for phosphorus. Why? Because it has got only 3 groups associated with it. That is, the 3 phenyl groups are associated. Now there is a carbon associated with phosphorus, but that carbon is associated because phosphorus has given its lone pair of electron. So it has donated a lone pair of electron to carbon. So this is a coordinate covalent compound, right? So this is a coordinate covalent bond here. Coordinate covalent bond. Okay, it doesn't affect the octet configuration of phosphorus because all it has done, it has donated the pair of electron. Okay, the valence electron has been shared with phenyl group and it has completed octet. For carbon also octet is complete. Okay, 1, 2, 3, you can see 1, 2, 3, right? So there are 3 shared pair of electron and the 4th pair is here, right? So its octet is also complete. So both, you can see in both the, for both the atoms the octet is already satisfied. For phosphorus it is satisfied because it has attached to 3 phenyl groups only, and this attachment is only because of the lone pair of electron and nothing else. For this also it is the same, okay, and it has also completed its octet configuration. There are 8 electrons here also, okay. See, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons for carbon. Here also 1, 2, 3, 4, 5, 6, right? 5, 6 and 7, 8. So there are also here, you can see it needs only 3 electrons from phenyl group, right, to have octet configuration. So here also you can see that octet is complete. Now this is allied. This allied now can have 2 resonating structures. This can also be case, right? See, this pair of electron has been donated here and it has formed a double bond. So another coordinate covalent bond has formed. So now there are 2 coordinate covalent bonds, one provided by phosphorus, the other provided by carbon. Now there is no effect on phosphorus, okay, its valence electron has been shared with this phenyl group, so its octet is complete. And there is no change in carbon also, right, because the pair of electron which was here is now here. So there is no change for carbon also. So 2 resonating structures are possible for your halides, and the resonance hybrid you can draw by yourselves what it would look like. Now in Wittig reaction, this structure only takes part. Okay, this structure has no relevance. In Wittig reaction, when this is converted into this, it would be this structure that would take part in the Wittig's reaction. So now let us see what is Wittig's reaction. So now we are going to start Wittig's reaction. In Wittig's reaction, what happens? Let me draw the reaction first. We take a carbonyl compound. 2 things before starting Wittig's reaction I would like to mention. This reaction is shown by carbonyl compounds, that is aldehydes and ketones. And the second thing that I want to tell is the product of this reaction is alkene. Now alkene can be either simple alkenes, it can be conjugated alkene, or it can be substituted alkene. However, firstly the product is alkene. Okay, then you can classify what kind of alkene it is. So there are 2 points. One, it is shown by carbonyl compound. The second is that it is an alkene. The product is an alkene. Now let us start how we will produce alkenes from a carbonyl compound through Wittig reaction. So this is the carbonyl compound, and you treat this carbonyl compounds with halides. So I have an halide here, this one, and we have this. This is C6H53, and which is negative? This side is negative, this side is positive. Both have octet configuration complete, but they are positive and negative atoms which are bonded by covalent bond. Now you go for the reaction. You can see here how alkene is formed, and we form triphenyl phosphine oxide. So this is triphenyl oxime oxide. Okay, this was triphenyl oxime, right? Sorry, triphenyl phosphine. This was triphenyl phosphine, and this is triphenyl phosphine oxide. Okay, so now we have got triphenyl phosphine oxide, which is a byproduct, and here we have got a substituted alkene. Okay, it is basically firstly an alkene. Here we have got a substituted alkene, a higher alkene. Okay, and that is by reaction of carbonyl compound with halides. Here if you see, the valency of phosphorus has converted to 5. Correct? Now it is not in 3 valency, it is in 5 valency. Okay, and there are no lone pairs here. Here the valency is 5 for phosphorus. Okay, so that is why we saw about valency initially. Okay, so this is the Wittig reaction. Now let us go for its mechanism. The mechanism of Wittig reaction is nucleophilic addition. Nucleophilic addition of halides to carbonyl carbon. Nucleophilic addition of halides to carbonyl carbon. There are two steps. Step number 1. Please note down that nucleophilic addition of halides to carbonyl carbon. That is the mechanism. 2 steps. Step number 1, which is formation of betaine. Let us see what is this. Is the main step. So let us see it. So for this I treat the carbonyl compound with halide. This is the halide C6H53. This is positive. This is halide. This is the carbonyl compound. Now carbonyl compound story is little different. The molecule is strained. This is very polar bond. So there is always negative charge here because oxygen is electronegative, and a positive charge here. And now to this positive charge, it is very obvious that this side would come and attach, right? And we get a product like this. So we get something like this. C6H53, this is C and positive. This is called as betaine. So what is actually a betaine? Betaine is an organic compound. It's a neutral organic compound because there are both positive and negative charge. It's a neutral organic compound where non-adjacent atoms are one of the non-adjacent atom is a positive functional group, which may be a quaternary ammonium compound or a quaternary phosphonium, and the other functional group is a negatively charged anion, which is a carboxylate ion. So such neutral compounds are called as betaine. What is a betaine? Betaine is a neutral organic compound in which two non-adjacent atoms are oppositely charged. One is the positively charged functional group, which is normally a quaternary ammonium compound or a quaternary phosphonium compound, and the other is usually a negatively charged anion, which is a carboxylate group. So such organic compounds are called as betaines. So here we have formed a betaine, and how we have formed, we have shown you. Now let us go to step number 2. Step number 2, elimination of triphenyl phosphine oxide. Let us see what is it. So we have formed a betaine ring. So this is the betaine ring here, right? And here there was CH2 and P C6H53 plus, right? Now what can happen here is that this is very unstable situation. So this pair of electron, it can come here and it can satisfy P. P is also positively charged, so it can form a ring, correct? So now we form a ring which is like this, C6H53. Am I right? Yeah. So like this we get a ring. Now look at this ring. There is a very distinguishing character of this ring, that is the two carbon atoms here are actually sp3 hybridized. So sp3 hybridized carbon atom should ideally assume a tetrahedral shape. It should ideally have a tetrahedral angle, that is the atoms or groups should be separated by an angle of 109 degree 28 minutes. But here the structure, the geometry of the molecule doesn't allow it to so. So there is of course bare strain here in this ring, and it is bound to cleave, and there is no doubt about it. It is bound to cleave. But when it cleaves, what happens? When it cleaves, see, this is oxygen. It is electronegative in nature. So it will try to pull the electron towards itself. When it cleaves, the electron will be pulled here. And what would happen? It would become negative charged, right? And this negative charged oxygen, negative charge over oxygen is not stable. So that negative charge would come here, right? And when it comes here, phosphorus, it has a limited valency. Maximum is 5, right? So its valency is complete, right? When it comes here, it becomes 6 actually, okay, if carbon is there. So what it does, it eliminates this pair, okay? So what actually happens when cleavage occurs, this pair goes here and this pair comes here. I hope you got it. So now we got like this. This is our alkene, and we got something like this, which is what we said in the title, triphenyl phosphine oxide. Here the valency of phosphorus is 5. That is why when we started the class we discussed about the valency of phosphorus. See, here the valency of phosphorus is 5. However, it is not, inert gas configuration is not achieved. And here we got a substitute, we got a alkene. Correct? Yes. Let us now we have got an alkene, reaction is over, the mechanism is over. Let us now look at an example of Wittig reaction. Wittig reaction example. So I am going to take acetone. Let me take acetone here as an example. Okay, and let me take this C6H53. And positive here, negative here. It's a neutral molecule where adjacent atoms are having positive and negative charge and they are bounded by covalent bond, that is an alide. Now what would happen? CH3, C, and we get CH3 here, and this CH2 comes here, and this oxygen goes there and becomes triphenyl phosphine oxide. So here, what is this? This is 2-methyl, 1-propene. 1, 2, 3. 2-methyl, 1-propene. So here we have got a substituted alkene. Here we have got a substituted alkene. If in this place, if I in the place of acetone, if I am using HC double bond OH, I would get ethene, CH2 double bond CH2, right? So I get an alkene. If I am using here, say acetaldehyde, okay, then also I will get a simple alkene. I will get a simple alkene, okay. If in this place, if I am using CH2H3C, then I will get a conjugated alkene. Right? Here also one CH3 will come. I will get a conjugated alkene. So that is the significance of your Wittig reaction. So we can make 3 types of alkenes. That is the significance. Number 1, we can make alkene, simple alkene. Number 2, we can make your substituted alkene, right? And number 3, we can make conjugated alkene. So all these alkenes, you can make through Wittig reaction. You can make a number of natural products. For example, you can make your vitamin A precursor, which is beta carotenoid. You can make through Wittig reaction. You can make lycopene through Wittig reaction. Lycopene is a powerful antioxidant. It can delay the process of aging. It can protect you against sunlight, and also it prevents heart ailments. So it's a very powerful antioxidant, and you can make lycopene using Wittig reaction. And there is one more which is called as bisabolene. It is used as intermediates for number of organic compound. This one, bisabolene, and there is one sweetener which is called as Hernandez-Dulcin. It's a sweetener, and the precursor of this sweetener is bisabolene, which is synthesized through Wittig reaction. So all these are uses of significance of Wittig reaction. Dear students, we have seen how phosphine compounds, organophosphorus compounds are used in the synthesis of alkenes. I hope you have liked the class and you have understood it. If you have done so, please do not forget to subscribe this channel. It would be a great support. Your support is a great encouragement to me. Please do not forget to like and share. Thank you very much.